Okay, good morning, ladies and gentlemen. Welcome back from your break. Just a few things before we start. You have tests coming up. Your test on organic chemistry that includes hydrocarbons and reactions of hydrocarbons will be next week on a day of your choice. Let's make it Friday, right? Friday is good? Yeah? Okay. So, all good today? Okay. So, second, you have two labs coming up. The first lab would be on week 3. That means the week following the next, and the one after that is week 4. So these are 1% labs, and I'll let you know what they'd be about, what they'd be on, by next week. So until week 4, you know that you have 3 assessments coming up. Now, what about the content? We have covered up till chapter 14. Up till chapter 13, we are on chapter 14, and after that, we just left with chapter 15. We just have 2 topics left. I plan to finish that off by week 4 because we have assessments. Otherwise, we would have finished it by week 3. And after that, I'm thinking of spending all the time doing past exams, and I'll try to source as many past exams as I can. So we'll go through that. So that should give you enough practice for the exam coming up. So today we start chapter 14, which is polymers. And today is just a brief introduction to polymers. I want to get into the depth of polymers only tomorrow, but we'll just get a brief introduction because, as I said, this topic is as new to me as it is to you. So today's lesson objective is to introduce the terms monomers and polymers and to expose students to a variety of natural and synthetic polymers, to provide a brief introduction to addition and condensation polymerization, and to differentiate between addition and condensation polymerization using suitable chemical reactions. Now, you'd be successful if you read page 146 to 149, Essential Chemistry, and as long as you manage to solve the problems that I planned for today in the class, that should be enough for today. Tomorrow you'll get the big stuff. So, polymers are everywhere. This thing that I have around my bottle here is a polymer. This is a polymer. The pen that you're holding, Luke, is a polymer. That pencil case that you have, Monica, is a polymer. This thing in which you got your muffins is a polymer. Your muffin probably is a polymer as well. I don't know how they are made because, yeah, the packet of chips that you have is a polymer. Adi, the spectacles that you're wearing, a polymer. Matthew, the shoes that you're wearing, probably a polymer somewhere in them as well. The wire that you have, the earphones that you have, Bree, polymers. Big T, you see that the cap that you have, probably somewhere there you have a wire which holds it firm. That's a polymer as well. So they are basically everywhere. Your uniform, I'm sure it's not pure cotton or pure wool. That has polymer materials as well. If you're wondering, there are a lot of times that you'll find that the clothes that you buy would say do not tumble dry or only use warm drying conditions. Why would they say that? Because they are made up of polymers which can withstand only a certain temperature. And if you use high temperature, there's a good chance that the polymers inside would actually start melting. And you don't want to burn your clothes. That's why you use a certain setting on your iron when you're ironing your clothes. Polymers are everywhere. When we used to have cotton or wool as our basic clothing material about 100, 150 years back. But ever since we have discovered polymers, it's everywhere. Your clothing, your food, packing material, sometimes your food as well, it's all polymers. Subway bread was criminalized or was maligned to have a polymer material that you use in surfboards. That was out in the news if you follow that. So now they've removed it, thankfully. But all those who ate Subway bread about 5-7 years back probably got some polymers in their body through it. So pretty much they're everywhere. So what is a polymer? A polymer, poly means many, mer means parts. So it's many parts. Again, Latin comes from the Latin name, plastic for that matter comes from the Latin name plasticus, which can be melted or molded, melted and molded. So, but how do we get polymers in the first place? And that question brings us to the discussion of monomers. Mono means single. Monocycle, which is just one wheel. Some kids are ride it around school, I've noticed. Monomer is just one part of the polymer. You actually start with just one part, and then through a chemical reaction that ends up to become billion parts, and that's how we get polyethylene or plastic or anything that I pointed out in the lesson initially. So just something easy to relate with. That's how actually polymers are formed. You just have few parts and you combine them and you might just increase the temperature or add a catalyst and boom. Put the two chemicals and give them the right conditions and they automatically form this long chain which we call polymers. And I'll show you a video which is really interesting, which shows how nylon is created. And if Lena has the resources, I'll probably do it because I found it really fascinating. So cotton, which is a natural polymer. Anyone knows what the building block of cotton is? How do you start? How if you break that molecule down into its simplest part, what is the part that is repeating itself? What is the simplest part that is repeating itself to give cotton? I'll give you some time to think about it. That the monomer or
mushroom clouds snake skyward, hurling the atom's deadly radiation high into the heavens.
Okay, this is the aqueous solution. I'm going to pour this in here. And that aqueous solution contains the acid, the diacid. And this is a solution of the hexane diamine. It's dissolved in hexane, and hexane is less dense than water. So this solution is going to float on top of the other one. And then where the two solutions come together, the interface between these two solutions is where this reaction is going to take place. How many fingers do I have? Anyway, here we go. Maybe these were gloves for another species. Okay, so I'm very carefully going to pour this down the side, and then where the interface is, we'll have contact between the diacid and the diamino hexane. The hexane layer is floating on the top here. But of course, where they come together is where the polymer can be made, where the condensation reaction is happening. So then I'm going to reach in here, and where the interface is, I'm going to pull out some nylon. So here we go. See how much nylon we can pull out of this thing. There's a meter or so. 2. There are records set for this, and so I think it's actually in the Guinness Book of Records. I'm sure we're going to beat that record today. What are we at, 4? 6. Now you can see that you can get a lot of material out of a very small quantity. I only dissolved a few grams of the acid and the hexane diamine in here, but we get a tremendous amount of material out of here. So on a large scale, this is done not with a whole bunch of people doing this, of course, but that would certainly be a minimum wage job, wouldn't it? Well, this stuff comes flying out of a machine as a thread, and it gets washed because this is actually quite an acidic solution. It gets washed to remove the acid. It gets dried, and then it gets spun into larger collections of fibers. I don't know how long I'm going to do this here. I obviously put too much of this stuff in. But on a large scale, the chemistry is exactly the same. So it's making of fibers which are then spun and made into fabrics. Oh, come on, this is getting ridiculous. Getting shorter too. Yeah. Yeah, you probably can just pick up a big loop. Well, anyway, there's many meters there. We probably got 20 or 30 meters of this stuff. You wouldn't have expected it out of a little bit of solution. And on a large scale, they make much finer fibers as well, too. So they get miles of this stuff, kilometers, I guess we have to say these days. So that's making, it stinks too. It's the diaminohexane that stinks. It's kind of like putrescine. Remember, putrescine was diaminopropane. This isn't too far off. It smells like a dead animal. So that's making a
from the video, we saw how nylon was created when you mixed two liquids together. But we still don't know what the chemical compounds are. They did mention it, but I'll show you the actual chemical reactions. Don't worry too much about it. Like I said, today is just a brief overview. I'm not going into too much depth. Tomorrow we'll actually be practicing these reactions by hand. So, moving on. Just a description of what you just saw. That is quite dangerous actually. The students holding the thread by hand, because it is acidic, so it will cause slight burns. So we need to be very careful when we're handling it. That's why I think in that case he's doing it right with the glass rod. But they are holding it, so I'm hoping that is washed. Okay, so what do you need? You need adipic acid, which is that molecule there, tetramethyl tricarboxylic acid, and hexamethylene. It's a favorite question for examiners. 966 is such an important compound that you will be asked in a 1 mark or 2 mark to give the chemical reaction which is responsible for the production of 966. It has always turned up in an exam, and it will continue to do so. So it's called a copolymer because it is of course made up by two different polymers, that adipic acid and hexamethyldiamine. They're two different monomers, for that matter, and two different monomers combined together, and there's a reaction in which the water is eliminated. And since the water is eliminated, we call this condensation polymerization. Remember condensation reactions? You had water eliminated when you had concentrated sulfuric acid in it. It's exactly the same thing. You combine two monomers, and there's a dehydration reaction in which the water is eliminated, and when the water is eliminated, you get nylon 6,6. Now, I've spoken for a lot of time now, so what I want you to do now is go through question 10 and 12 from set 20 and see how you go. Thank you.